When we were looking at samples last couple days, we had two sets, two groups, group A, group B, upriver, downriver, juniors, seniors. But sometimes I look at a before and after test. And I'm looking at the same object before or after, the same person before or after. Or I've got a matched idea, or I've got an A-B decision. You tell me, do you like this one or this one? Well, then the samples somehow are paired between them. And this means I'm going to try and create this idea for comparison by looking at the difference between the objects. So, like before, I'm thinking of for each member, I'm going to create two measurements, like the before treatment and the after treatment idea. I am going through physical therapy for my shoulder. When I do these exercises, is my range of motion greater or lesser than before I did the exercises? So we measure the range of motion before, we measure the range of motion after, and we construct the difference between the two. So I built a new variable. And now I'm going to use that variable. And I'm going to do a one variable test on D as a method of comparing the before and after, the X1 and the X2. So if I'm doing a one sample idea, that's what we were doing in chapter 9, I'm going to look at the average and the standard deviation for that. So I'm going to say I need D bar. And I need the standard deviation for D, S sub D. Now, clearly, I won't know the population standard deviation. I'll only know the sample standard deviation. And if I have a benchmark, which I'll call mu sub D. We called it mu 0 last time, the average I think I should be getting, my benchmark value. Then I can do a t-test. And now I'm back in the last chapter. In the homework I just gave back. And I say to myself, okay, well, then I know the degrees of freedom is the number of differences I have, the number of pairs of data, minus 1. And I can do a t calculation. With my standard error. This is the exact same calculation we did in chapter 9. So, here's an example. Are daughters typically taller than their mothers? Problem number 13, page 382. At alpha equals 0.05, there's my significance, does the following set of samples show that daughters are taller than their mothers? Of the daughter's height, of the mother's height? for 7 different families. I clearly have to have pairs. I couldn't go comparing you with my mother. That wouldn't do me any good. I need to compare you to your mother. I need to compare you to your, and it doesn't count for you at all. It's only about daughters, right? So I need to be able to work with daughters and mothers. I've got to go to families that have daughters. I've got to be able to get measurements right now for both of them. I can only do that for 7 families this time. So the first question I'm going to ask before I actually do any sort of testing at all is I need a null hypothesis. I need to know, what should I be testing for or against? If I think about the setup here, D, my variable, is the difference between these. And in my table, daughters were the first group and mothers were the second group. So if I'm asking, are daughters taller than their mothers, I'm asking for group 1 to be bigger than group 2. I'm asking for D to be a positive thing. So in this problem, problem number 13, I want to be thinking about my null hypothesis and my alternate hypothesis. And my alternate hypothesis is that the average height distance is bigger for daughters than it is for mothers. So I want to claim that this difference should be positive, and that's the unusual kind. And my null hypothesis will be, no, there's really no difference, or maybe it's even the other way around. Hey, wait a minute. With this setup, left tail, two tail, right tail, which one am I doing?
Right tail.
Bigger than, this is a right tail. Now, I can do this a couple different ways. The first thing I could do is attempt to do this all by hand, which would mean I need to give it the data, right? So I go back here and I start saying, okay, we want to look at the difference in height between the first and the second. And I always take the first minus the second. That was my setup for the one-tailed difference. 67 minus 72 is -5. 66 minus 62 is +4. I can create a new list of data, right? So the D numbers I am looking at, I'll have 7 differences. And really what I need you to do is take a standard deviation and an average for these, right? I'm already doing a lot of calculations. Why do I want to do? I don't want to do these by hand. Let's not do them by hand. So in Excel, here's my data. That's the wrong data. There we are. There's my height data. So there's my height data. I'm going to do the same thing I did last time. I'm going to highlight my column. And I'm going to go to data and tell Excel to do the analysis. And the analysis I'm going to do is a t-test. And there they are right at the beginning there. And we see the t-test for 2 samples, assuming equal variance, assuming unequal variances, but above that, I see paired samples. It's explicit. There's my paired 2 sample. So I'm just going to tell it, I want you to do a paired 2 sample. Okay. And again, it says, okay, where's data 1? Variable 1 is here. Enter. Variable 2 is here. I've highlighted the word daughter and the word mother. So here I'm going to click on labels, that I am doing this with labels. And what do I think the difference should be? What's my benchmark here for the difference? Within my null hypothesis, what am I comparing to? Or greater than 0, right? My null hypothesis is less than or equal to 0, and my alternate hypothesis is bigger than 0. But that means I'm comparing to 0. So I'm going to type in here where the mean difference is, that I think the difference should be 0. Alpha is 0.05. If they gave me a different alpha, I'd put it right in there. Significance is given. And I want you to put this information on a new piece of paper, well, a new sheet. And here's all the information it gave me. Now you'll pardon my bluntness. What the fuck is this? So what I've got here are the 2 means and the 2 variances. And there were 7 in each group, which is good because they're a paired setup. So degrees of freedom is 6. It did the t calculation for me. Which one of the numbers up there is the calculated t value? T stat. They don't call it t calc. Excel calls it the statistic. So this is the number it gave me. 1.92. Much closer to 1.93, right? 1.299. I'll give it 1.93. Okay. If I have a critical value, I can make a decision. Again, Excel gives me that critical value. It also gives me a p-value. So I can use either option to create my decision. If I'm in the rejection zone, my t-value, doing a left, right, or center again?
Right.
So if my calculated value is big, it'll be in this itty bitty window right here. My calculated value is big, then I should reject. Bigger than what? Bigger than whatever the critical value is. Felix? But what is my critical value? Up there. T critical, 1 tail. Right there. Is my stat value bigger than my critical value? We fail to reject, and that means I cannot conclude from this data that daughters are taller than their mothers. It is possible, and on average, this group of daughters has a height of 171.3 centimeters, and this group of mothers has a height of 165.4, but it isn't different enough that it couldn't have happened by random statistical variation. It's just this sample isn't enough. So I failed to reject my null hypothesis. Here I do not see that daughters are taller than their mothers. Is it close? Yeah, that's really close, isn't it? 1.9299 versus 1.943. That's really close. Another way to look at it is to look at the p-value. The 1 tail p-value is here in the middle, 0.0509. And my 0.05 was my cutoff. If it had been any smaller than 0.05, I'd say reject. I got 0.051. Just barely squeaked by, not rejecting. This is a real close call. If I'd picked any other alpha value, 0.06, I might reject. So this is where our significance, our decision on how tight to hold this result matters.
Yeah.
Questions? I hate doing this crap by hand. I don't think it's worthwhile. As a matter of fact, you'll see in several of the questions asked in this section, you'll see the output given. Hey, I did this in Excel. Here's what it shows me. Tell me what the answer is. I'm not here to make you crunch numbers manually. That's a waste of your time. If I've got this technology, I should use it. I need to be able to take the answers out and understand what's going on. Questions? High school athletes in a swim competition. Problem 17. Same idea. Individual team, the times in the 200-yard individual medley are typically more than half second faster than the times going into the meet. So when you qualify for a meet, you go and pre-run the race. They say you meet the qualifying time, but it turns out that people preliminary, this is the actual race, this is their seed time. Did they go up by more than half a second? Okay, wait a second here. Did they go up by more than half a second? I've got a different kind of null hypothesis. What's my null hypothesis in this setup? Except that my null hypothesis would be there isn't a difference, right? Times didn't go up, right? Now, if I do, so I need to figure out which way I'm doing the subtraction, right? If I do seed time minus meet time, which one do I think should be higher? The first one or the second one? Oh, because I want times to go down, right? I want people to get better. So if I call this x1 and this x2, then the difference should be negative, right? So I should say to myself, oh, I want the null hypothesis to be that the difference is, wait, no. I want the seed one to be higher, right? I want the times to go down. I want the difference to be positive. So I want, sorry, mu d to be positive. I want the times to have gone down, which means that the difference will be a positive number by at least half a second. And that means that's my alternate hypothesis. So my null hypothesis is that the difference is less than or equal to half a second. Okay. That's not zero, so I got to remember that when I go do the numbers in Excel, that my hypothesized mean difference is 0.5. By the way, that simply means that what they're going to do in the entire set of data behind the scenes is they're going to subtract a half a second from everything and then do it as if it was zero. So again, I don't want to do this garbage by hand. Here is our swim data. Swimmers. Seed times, race times, and I'll do the same thing. Data analysis, paired samples. Only this time, I don't just want these numbers. I want all the numbers for the entire race. Yes, thank you. I need to change the other set of data too. Make sure it goes all the way down. My hypothesized mean difference now becomes 0.5. Alpha is still 0.05. So I do the test. You tell me, does this set of race times support the idea that times went down at least half a second? Do I reject my null hypothesis or do I fail to reject
Right tail test.
it? It's still a one-tail test.
The teacup is still bigger, but it's bigger than the crystal belly. So we reject.
Because I'm up in that tail region. I'm too high. I'm in the rejection zone, which means race times did improve. My swimmers did better during the pressure of an actual meet. The other way I could get the same answer is to look at that p-value for a one-tail test, right? Notice it doesn't tell me whether I'm doing right or left because it just folds the thing over and assumes I'm doing it right all the time. That's less than 0.05. 0.05 is my cutoff. I must reject my null hypothesis. Times did go down, and that means the difference is at least a half a second. Yay! Now again, depending on what technology I have available to me at any given time, I can do this in a lot of different ways. We did two sample t-test just now. There's my two sample t-test. And this is the data we were using on Monday with our GPAs for juniors and seniors. But I could put in the averages I knew. If I wanted to give it the actual data, I could tell you which list was where. But you'll notice what's missing here. There's no option in this that says paired. I got lots of tests in here. But what I don't have is a paired anything. There's nothing in any of this that says paired. So if I wanted to do this paired, I'd need to do a one sample test on the differences. I would need to do this test, not the two sample test. So knowing that a paired test is really a one sample test means if I'm without Excel, I can still do that, but I have to do it as a one sample on the differences. I'm going to do it in Excel a whole hell of a lot more often. Questions? Talk to me. Okay. Same idea holds true for proportions. If I am comparing the proportion of people who want to vote on an issue in one way and then they see a commercial and then I ask them again whether the commercial makes them vote more for it or less for it, I could check the proportion. So if I have two different population proportions, then what I'm really going to test for is the difference between them. And again, just as I did before, I can ask, should this be zero? Should this be some difference? Usually I'm testing against zero. So something like, we did this exercise regimen and 20% of people lost weight, lost more weight doing it than without it. So I want to know that the difference is 0.2. So I'm going to say, just as before, I have three different versions of my null hypothesis. And three different versions of my alternate. And again, I look at the alternate hypotheses to tell me what kind of a test I'm doing. Now, fortunately for me, when I am doing proportions and we're comparing, excuse me, to zero, I then look at the proportion from group one and the proportion from group two. And I'm going to do for each group, I'm going to get a proportion, the number of ways it happened over the number of people in each group. And I can, just as I did with my variances, I can pool my samples. We did this with a pooled variance. Well, when I do a pool behavior, I get a combined proportion. PC. C for combined. And then that's x1 plus x2 over n1 plus n2. That's not the same as just adding the two proportions. If 20% of group one did the thing I want, 30% of group two did the thing I want, I don't just add the 0.2 and the 0.3. If I have large enough numbers, N1 and N2 are sufficiently large, and X1 and X2 are sufficiently large. We'll talk about what large enough means in a minute. Then the central limit theorem comes back and I say, oh, well, we're using normal stuff. When I'm using normal stuff, what distribution do I use? Which means I use z-scores, because normal distribution comes with z's. Now, that means I need a z-calculate. Z-calculate takes my difference, in this case, P1 minus P2 minus my benchmark, but my benchmark was 0, and divides by the standard error. Standard error has a square root in it. When I'm dealing with binomials, when I'm dealing with normal distribution, with the square root of n, right? Okay. But because I'm using this pooled proportion, the standard error looks like the error for the binomial distribution. Square root of n on the bottom, and then proportion times 1 minus proportion. That's the same error we were using in our binomial distributions. Okay. I'm going to do the same thing I did for all my z-tests. I'm going to decide if I'm doing a one-tail or a two-tail. I'm going to write my null hypothesis. Do I want it to be greater than or equal to, exactly equal to, or less than or equal to? And then I'm going to do this. And I'm going to look at the z-table, or the numbers I already know, right? 1.645, 1.96, 2.326. I've got all these numbers I use all the time. Problem number 23. Pick one, A, B, or C. I don't care which one. We're going to do one of them. C. C is about first-time visitors in Hawaii at 2 different hotels. I don't know what they're asking them, but they did a survey of all these people. And out of group 1, there were 80 people. 20% of them answered favorably. In the second group, there were 75 people. 32% of them answered favorably. And I want to do a left tail test. So I think that the average proportion for group 1 should be less than the proportion for group 2. That's what a left tail test is telling me about. Now, it didn't actually give me the data. It gave me the summary statistics. So I'm ahead of the game here. 23C. Proportion number 1 was 0.20. N1 was 80. Proportion number 2 was 0.32. And 2 was 75. Alpha equals 0.05 left tail. It told me specifically to do a left tail. So my null hypothesis and my alternate hypothesis, that should be H1. I get so used to writing pies. My alternate hypothesis is on the left, pi 1 minus pi 2 is less than 0. And I'm doing alpha equals 0.05. One tail, alpha 0.05. On my z scale, what's my critical value? Almost, because I'm doing a left, but 1.645. Okay. I am assuming for the moment that these are large enough groups. So I'm going to combine my proportion. How do I get PC? My combined proportion. Wait a minute, there was a formula for that. What's the formula for PC? Problem is, I don't know what X1 and X2 are. But I know how to get them. I do? How? Where did X1 come into play? Where did X1 show up? What formula? Right. So X1 shows up in the proportion formula for P1 and X2 in the proportion formula for P2. Oh, wait a second. P1 is X1 over N1, right? And I have P1 and I have N1. 0.2 is equal to X1 over 80. I can solve for X1. What's X1? Exactly. X1 equals 0.2 times 80, which is 16. Same thing for proportion 2. Proportion 2 was 0.32. 0.32? Yes. And N2 was 75. So what's X2? 24. Great. And now I can do the combined proportion. PC is 16 plus 24 over 80 plus 75, which is 40 out of 155. Give me a number. And we could go as many more decimal places as you want. It doesn't end there, but that's good enough for right now. Now I have a calculated Z value. Proportion 1 minus proportion 2 over my standard error. Square root of 0.258, 1 minus 0.258, 1 over X, I'm sorry, N1, and 1 over N2. Calculate a number for me. So I'm going to do the subtraction on the top and I get negative 0.12. And then I'm just going to type in everything on the bottom under that square root. 258, 1 minus 0.258, 1 over 80 plus 1 over 75. Type all that in and what do you get? Ah, okay. I want the whole thing. So then you take 0.12 and divide by that. Wonderful. Now it should be negative, so make sure you didn't drop the minus sign on the top. Because 0.2, okay, perfect. Now, wait a second. Somewhere I have a critical value. I wrote that down. What was my critical value? 645. Great. So here's my question. Reject my null hypothesis or fail to reject it? 1645, 1.7, it's further down. Negative 1.7 is further left than 1.645. We're in the rejection zone. Out we go. What does that mean? It means whatever question was going on here, the difference between Hotel 1 and Hotel 2 is statistically significant. I don't know what the question was because the stupid book only told me, hey, we're comparing two hotels. You like the view out window 1 better than window 2? I don't know. The bar serves better drinks. The restaurant has better appetizers. I don't know what the hell they're asking. The beds are softer. My brother works for a travel agency. He deals with this sort of all the time. But those are the sorts of surveys you get. But now I know, yes, whatever the difference is between Hotel 1 and Hotel 2, it isn't random. It's statistically significant. Questions? I did make an assumption to do this. I assumed that everything was large enough and we were allowed to pool our proportions. How do I know if it's large enough?
Bigger,
And
minus.
which is the same thing we were doing when we checked for one sample proportions being normal. So I'm just checking to make sure all of my numbers, both successes and failures, are at least 10. So back up here, we have 16 successes out of 80. That means I've got 64 that went the other way. That's still bigger than 10. I'm good. I had 24 out of 75. Means I've got 51 that went the other way. Both numbers are bigger than 10. I'm perfectly happy. If they're not normal, if I don't have enough, then I wouldn't be able to do this using a z-distribution. Like the last question on the homework I just gave back about the eggs, I'd have to use the binomial. Ew. Trust me, that's even worse in terms of software. I can do all of this in Excel when I actually have the data. When I do the binomials, I want to use better software. Things like SPSS or Ministat or lots of other pieces. I really would much rather do that problem that way. There is an example in the text about this. I don't think it's worthwhile at this point. We've seen how to do it with one sample. It's good enough. I can also do this if I believe the proportion to have a non-zero difference. We did say that we were benchmarking against 0 here. If I think that that difference is at least, I don't know, 0.1, there's at least a 10% improvement. I get ads for that for study aids all the time. If you study with our program, your grades are going to go up by at least 10%. Sure they are. I can check. I just have to adjust my differences, subtract 0.1 from all the differences, and I can move forward from that. Questions? I'm not going to do the ones with non-zero proportion differences. I think it's more work than it's worth. Just like I did with means, I can do confidence intervals on proportions. But notice that the formula for the confidence interval is the same formula it was for means and for one proportion. The number I'm thinking is my actual mean, plus or minus z alpha over 2, because we need to go both directions. I need to do alpha over 2, left and right, and my standard error. Notice there's no combining this time. P1 and N1, P2 and N2, they're separated, but it's the same proportion. And again, I find this to be particularly helpful. There is a lovely example on page 391 that goes through this. I've got 1 minute left, so I'm not going to do it for you. The only other thing I want to do comparisons on is standard deviations themselves, because I want to understand where the variance in my populations comes from. So I'm going to start talking about comparing variances on Friday. When I do that, I need a new test. I need a new distribution. We'll talk about that on Friday. I will see you all then. Have a wonderful rest of your day.